This presentation is part of the Interreg 2C's SolarRise project and is about photovoltaic systems from design to operation. In this presentation, we will look at the basic principles and operational design of PV systems. We will look in more detail at the design of those PV systems and then investment, operation, and maintenance. So the basic principles of photovoltaic systems is that solar panels, they convert solar radiation into DC electrical power using the photovoltaic effect. Then an inverter is needed to convert that to AC electricity. A modern inverter has multiple functionalities. You have maximum power extraction from the PV modules in an array using a maximum power point tracker or MPPT. The inverter also converts the DC to AC electrical power for use on the grid, and the inverter only delivers power to the users or the grid after checking all safety requirements are met. If we look at the generation profile over the different seasons in Northwestern Europe, we see that the summer maximum power is approximately 3 times as high as the winter maximum power. And this is mostly because the sun is higher in the sky. By contrast, the spring and summer monthly energy is around 5 to 6 times as high as that of the winter generation. And this is again because the sun is higher in the sky, but also that there are more hours of sunlight in the longer months. With all of this, we do need to consider the mismatch with the electrical energy consumption patterns, that usually in winter the demand is higher because of more lighting and heating needs, whereas PV generation, as just shown, is lower. In summer, the demand is usually a little bit lower. You have reduced lighting needs, typically no heating needs, and in some cases limited cooling needs. But PV generation is significantly higher. And so this matching of electricity demand with electricity generation, these issues need to be considered in the design of PV systems to achieve a cost optimal effect. If we look at the PV response to irradiance or sunlight, the current essentially increases linearly with increasing sunlight. If you look at the numbers at the bottom of the graph, you see that for increasing irradiance, the current that you get out of a PV module increases linearly. The voltage sees a relatively limited change, but it does drop quickly below 100 watts per square meter, and the power increases linearly from around 100 watts per square meter. The conclusion of these three things is that irradiance matters, and that you need to avoid shading and you want to maximize sunlight capture with both the tilt and the orientation of PV modules. As you can see in this video and the animation to the right, PV modules can see significant power loss and efficiency loss due to shading. And as you can see in the still version now, you have up to 60% power loss of a PV module as a result of thin poles falling on the shading of those thin poles falling on the modules. And if you then connect multiple modules in series, which is the standard situation for photovoltaic systems to achieve a higher voltage and less energy losses, if one of those modules is then shaded, it affects the whole system. And so the shading consideration from permanent nearby objects, such as buildings or trees or chimneys, must be incorporated into the design. When we're looking at the PV response to temperature, the efficiency of PV modules decreases with rising temperature, which is approximately 0.3% to 0.5% per degree centigrade higher, which means that a temperature of the module being 10 degrees higher results in an efficiency drop by about approximately 5%. As a result, the total system efficiency decreases in summer and is higher in winter. But again, you have more hours and stronger sunlight in summer, so the overall output is much higher. The ideal combination would be to have the hours and amount of sunlight as you see in desert areas with the temperature that you can see in Antarctica. And then you would have the best of both worlds of both hours of sunlight as well as low temperatures for highest efficiency. PV systems age, they get older, and that age affects the PV systems. One of those aspects is the performance loss rates, PLR or degradation, which is the decrease in efficiency of PV modules and PV components in a system. And that reduces the energy yield of those systems over time. The other thing that happens is the failure of PV system components, such as modules, inverters, or cables, which can result in very high power losses if they happen. It is known through the experience to date that 20 to 25-year-old PV systems are expected to have more than 80% of their initial power, which corresponds to an annual PLR of 0.5 to 0.67% per year. With this, the current PV module lifetime expectations are 25 to 35 years. However, lifetime was defined as the PV performance being greater or equal to 80%, and PV modules can still produce power afterwards. Inverters, on the other hand, they have had a 10 to 25-year lifetime, and there it's necessary to plan for replacements of inverters for the future. Now, if we do a PV system performance analysis, we need to match the energy yield of the system as it experienced the weather. And therefore, you need to compare the measured performance to the measured weather. And the actual PV performance will naturally deviate from standard testing conditions for which the data sheets of PV modules and inverters are made. And here, monitoring is needed to distinguish between normal, expected behavior and issues occurring. There are two main monitoring measures used by owners. The first one is the absolute energy yield per year, measured in kilowatt hours or megawatt hours, which is essentially a proxy for the revenues, which is measured using the electricity meter. The other measure is a relative energy yield, which is obtained by the performance ratio, or PR, which is a measure of the system quality. It is the ratio of the measured electrical energy scaled by system power, so that you can compare a 5 kilowatt or 100 megawatt system to the received insolation. And that is measured using a pyranometer as well as the electricity meter. With the cost of a good pyranometer being €1,000 to €3,000, it is clear that these are typically used for larger, more expensive PV systems, whereas residential systems or smaller commercial systems rely on the absolute energy yield. With all of this, monitoring on a daily, monthly, and yearly basis is key to see if there are outages or to catch underperformance. As you can see in this image, the blue dots show the performance ratio throughout the year, and that can vary quite a bit. However, there are methods to correct the performance ratio so that you can evaluate the system performance at other times in the year. Now, the performance ratio evaluates the performance of the actual PV system versus an idealized system that operates at standard testing conditions. And those standard testing conditions are used to measure and quantify the power of a PV module in laboratory conditions. where the module temperature is 25 degrees centigrade, the sunlight intensity that falls on the module, or irradiance, is 1,000 watts per square meter, which corresponds to the irradiance that you can find around noon in summer. And the spectrum or color of the sunlight that falls on the PV modules corresponds to what you can see close to the equinox in autumn or spring. With this, a 400 watt peak module will deliver 400 watts under STC conditions, and that is what is reported in datasheets. As we saw before, if you have less sunlight falling on your modules, you will also have less power from those modules. And also, as we saw before, that if your module temperature is lower, as in winter, the performance ratio will be higher, and in summer, the performance ratio will be lower. For Europe, a new and well-designed and correctly installed PV system should have a performance ratio greater than 80%, possibly up to 90%. And as you see in the source, corrections to the performance ratio are possible. If we now dive a bit deeper into the design of PV systems, in this image you see the different steps that can be done to model the performance of a PV system, all the way from sunlight to AC electricity. And all of those aspects also need to be considered for a good system design. If we look at a high-level view of a PV system design, you first determine the required or desired PV system power through the energy needs based on an initial estimate using tilt and orientation, yield statistics for a certain site. You then evaluate the environment, whether you have enough space available, if it is on a roof, whether the roof is strong enough, as well as possible shading objects. You then look at the connection limits and requirements associated with that. For example, the physical and electrical distance to a connection point and local regulations for connections. For example, that's for single-phase PV systems, the maximum allowed power is typically 5 kVA or 5 kilowatts, whereas 10 kilowatts on three-phase systems is allowed. And you need a grid connection study above a certain power level, which is often around 30 kilowatts. You then select the inverter and the modules. There you need to match the number of modules to the inverter voltage, power, and current needs. And you look at the logical installation of those modules and inverters for good operation and maintenance. And then you calculate a more detailed PV system yield and you determine the financial viability of the system. For the PV system yield, it's typical to calculate the 1 year or first year yield as well as the lifetime or 25-year yield. And if you do 25-year yield, that you include degradation. And then that you look at the financial metrics such as a payback period, the net present value or NPV, and the internal rate of return or IRR. If we look in a bit more detail, this is an example for Belgium where you can see that the best yield or 100% can be achieved for a PV module or PV array oriented due south with a tilt angle of 30 to 45 degrees. However, for the best morning or evening consumption match, the ideal is that half of your system is oriented at an angle of 45 degrees east and the other half 45 degrees west. And with that, you manage both the achieve maximum production in the morning as well as maximum production in the evening. Once you have that, you determine the required PV system power through the energy need, where you look at the self-consumption, if it's residential or commercial system, where you look to match the annual or monthly energy requirements. For front of meter systems, where you just sell all of the power to the grid, There, the design is as far as the budget and physical space permit, of course, balanced by the financial metrics. But all of this needs to be balanced by the connection limit. For residential single-phase systems, that is max 5 kilowatts. Residential three-phase, the maximum allowed power is usually 10 kilowatts AC. And for commercial or industrial systems, there it depends on the connection. And there it's usual to consult the distribution system operator, or DSO. And there it depends on the connection that a system has to the grid, whether it is low voltage, less than or equal to 400 volts, or medium voltage. If it happens that the PV power that is going to be installed is higher than a limit for the DSO, which is typically around 30 kVA, then a grid connection study is needed. And that usually results in extra time and cost that needs to be planned for. And then, once you have passed those steps, you need to select the inverter and modules. And if you look at a typical PV module, currently these power of PV modules ranges between 300 and 450 watts. And let's say that we select a 350 watt module. You then select an inverter with the AC power less than or equal to the allowed connecting power, and then you calculate the number of modules per inverter. For example, if you have a 4 kVA inverter and 350 watt modules, you get around at 11.4 modules per inverter. And there you need to round up or down depending on the space and budgets available, as well as the inverter voltage limits. In some cases, you're better off having 12 modules. In other cases, you're actually better off having 11 modules. Then you calculate a more detailed PV system yield, and you determine the financial viability of the system. For the PV system yield, you look at the first year and the 25-year yield. And for the 25-year yield, there you must include degradation. And there, a special form of degradation is LID, or light-induced degradation, which happens when PV modules are first exposed to sunlight. And that happens in the first days or hours in sunlight. And module power warranties that you see in datasheets, they typically start at 97 to 98% of module power, which essentially corresponds to 2 to 3% LID, and then they decrease by 0.5% to 0.7% per year. Then, when we're looking at the financial metrics, if you look at the payback period, there you need to estimate the replacements as well as maintenance costs. And then similarly, you can do the same for the net present value and the internal rate of return. If we now look at some of the design and installation do's and don'ts, you need to avoid mixing tilt angles and orientations on a single inverter, as a different orientation will mean that that module produces power at a different time of the day than the rest, that is mismatch, and that reduces the power of the full array. So do look to install all modules with the same tilt and orientation per inverter, or maximum power point tracker if an inverter has more than one. Moreover, don't use all of the space, much shading can happen. For example, in this case, these PV modules are very close to that chimney, so the likelihood of shading happening both in the morning and the evening on the array is very high. So make sure to leave enough space or avoid or reduce shading on modules. If we now look at the investment, operation, and maintenance aspects, for the investment in PV, installing PV is context dependent in that you need to look at the available space, the shading that can happen, the grid connection, also the demand profile over the year. Do you have a day or evening peak? Is there a summer or winter peak in demand? But also the customer profile and the system size. Is it a small or residential system, or is it larger, which needs a grid study? Usually when we're looking at components, modules, inverters, and mounting systems, they are generally of similar quality, but there are some negative exceptions. There are, however, some very large differences possible among PV system installers. The first difference that can be observed is the price, that you have, say, 1 to 3 euros per watt for an installation in Belgium, 1.5 to 4 euros per watt in France. So you can see a total system cost of around 5,000 for 3 to 5 kilowatt peak systems. The other issue is the quality of installation, as studies have demonstrated that more than 20% difference in energy yield can be seen between the best and the worst systems in Belgium and in France, and also the quality of the post-installation support. For example, if an inverter sees issues, how responsive is the installer to help sort those issues? With this, due diligence is key, that you need to have price discovery. So it is recommended to obtain at least 3 different quotes from different companies, that you also investigate the company guarantees and insurance that is offered, that you check the installer financial health, and that you ask common sense questions. For example, should those modules be so close to that chimney? Is that cable that I see running over the roof, is that protected? If we now look at maintenance, there you need to check the energy yield at least once per year, and if you can afford it and have a pyranometer installed, the performance ratio, and ideally more often, that you check the performance of the system, and that you also compare the actual yield versus the expected yield. And those can be values that you get from installer or from software. For example, for standard PV systems oriented either southwest, south, or southeast and correctly installed, there you can expect to have around 800 to 1,100 kilowatt hours per kilowatt peak per year. That means that a 5 kilowatt peak system should produce between 4,000 and 5,500 kilowatt hours per year. As to module cleaning, this is rarely needed, but there are some exceptions. For example, bird droppings or localized pollution, that a PV system is near heavy traffic, mining activities, or near a factory. And then if module cleaning has to be done, you need to avoid spraying water on hot panels because the glass can break from thermal shock. So in those cases, it's best to clean modules early in the morning. And you need to avoid using hard water or water that contains many minerals, and you need to ensure that you remove the excess from those modules so that the water does not pool or stay on the module. In summary, PV systems are flexible and modular, and if we look at those basic design principles, you need to install modules in a shade-free environment, you need to aim to match the consumption with PV power production during the day as well as the year. The PV module and the inverter characteristics, such as the power and the voltage, they must match, because otherwise you have avoidable losses. And a good rule is to have one tilt and orientation is one inverter or one maximum power point trackers. Some inverters have 2 or more maximum power point trackers, and as such, those inverters can have multiple orientations. As to system performance, there the energy yield and the performance ratio are aspects that need to be investigated and evaluated on a regular basis. Important to remember with all of this is that PV is an investment with low maintenance, but it does require maintenance. When it comes to asking quotes, you need to obtain at least 3 quotes from installers and perform due diligence on those installers. And module cleaning is generally not needed. And as a reminder, do not spray water on those when the PV modules are hot. You need to check the performance at least once per year and ideally monthly. You also need to expect wear and tear of your components, especially inverters, over a 25-year system life. You also need to compare the performance against the estimate or the forecast and know reasonable values for your installation and your region. Lastly, these are the references as shown and used in this presentation. Thank you for your attention.